Morning, everybody. I did a bad job yesterday. This is Alex. He's going to be our TA for the course. His office hours are on the syllabus. Cool. The first homework is posted after today. You should be able to get a good jump on it. We'll cover some stuff on Friday or tomorrow that we'll need, but should be able to get a jump if you're got a lot of free time today. Any questions from you? We'll display it rendered, but you can't interact with it. So if you want to play with the notes, then you'd have to run those notebooks locally. You can clone the course repo, fire up Jupyter Notebook in there, or fire it up above and then go to either your repo or that one. Yeah.
Just like a friendly reminder, if you delete something in your notebook, it's deleting your actual thing too. So just keep that in mind.
Oh yeah. It is connected to your real file system. So that was what you were referring to.
Yeah.
Yeah. Yep.
Huh? I don't want to talk about it.
All right. So today we're going to talk about data. So the types of data that we're going to work with, and we're going to start talking about how to understand data. By the end of the class, we'll be doing a little bit of calculus. So I know everybody's excited about that. Yeah. So we're going to talk a little bit about sort of two families of statistics. We'll talk about descriptive statistics and inferential statistics. The first thing we need to talk about before we can process and understand data is to understand the types of data that we're going to be working with. Right? And there's a few different ways we can sort of categorize the data we'll deal with. So the first would be discrete versus continuous. So you can tell me the difference between discrete and continuous data.
Discrete is a moment in time. This continues to flow.
So they do have temporal definitions. For our types of data, probably that's not usually the distinction we want. But the time definition gives us a little bit of insight.
I guess if it was like a number line, like 1 through 10, continuous would be all the numbers, and 1 through 1, all the numbers in between, and then, or sorry, that's continuous, and then discrete is just like 1, 2, 3.
Yeah. So the discrete variables are countable or enumerable is one way to think about it. So the integers would be a set of discrete things. Right? There's maybe one way to think about it is there's gaps between possible values. Okay? Continuous would be things where any value in range is possible. Okay? So a few analogies: a discrete musical instrument would be a piano. A continuous musical instrument would be a trombone. So you can put this line any length. Right? Piano, you can only hit certain keys. In terms of the data that we deal with, what are some examples of types of data that we might measure that we would call discrete? Year. So year could be a discrete thing. What would be a continuous analog to that? So year is kind of a discrete version of time generally, right? So time would be more continuous, right? We can, we're limited by our precision. So, when we represent things in a computer, you could argue that anything we measure is discrete because there's only, so many possible values we can represent in a computer. But, if we're dealing with floats, we're talking about continuous data. we're not just talking about the representation, we're talking about the types of things that make sense to do with that data, right? If we have floats, it makes sense to take the average. If we have years, maybe the average doesn't make sense so much. Okay, and so year versus time, how about some other discrete types of data we might be interested in?
Types of count, can't have partial number of people in a classroom.
Yeah, so we count, counting things, the discrete values. We roll a die or some dice, right? The outcomes would be discrete values, right? Whereas if we, I don't know, threw something in a dartboard, depending on how we measured it, maybe that would be continuous. Cool. Any questions about discrete versus continuous data? Once we talk about kind of analysis, the types of things we do with the two, with discrete versus continuous things, be different. When we're dealing with continuous stuff, we tend to deal with calculus, right? Maybe not directly, but we might not have to be doing calculus ourselves, but the tools we use are built on calculus, typically. Okay? When we're dealing with discrete stuff, it's more like number theory kind of stuff. So, the tools that we use are pretty different. All right, so those are the two types of variables we'll deal with, discrete or continuous. And then within those, there another way of thinking about the data we measure is by thinking about sort of what the possible values represent. Okay? And there are sort of four categories that we're interested in. So we have categorical, ordinal, interval, and ratio. So categorical data would be something like gender or color or where the values are different from each other, but there's no ordering between them. So if I have categories for red, green, and blue, there is no ordering between them. Right? They're different, but one is not bigger than the other or anything like that. So the categorical data, we get identification, right? We know which category something is in or which category our data point represents, but all we know is that things are different. So that's categorical data. Ordinal data would be where there is an ordering between our data, but the distances between things aren't really meaningful. Okay? So example of ordinal data that shows up a lot are the little scales you get on like your teaching evals that you fill out, or your any sort of like feedback form you fill out, or survey from likely to certain or unlikely to certain, that kind of stuff. You have these values, so certainly some of the time is less than most of the time, but the distance between them doesn't really have a strong meaning. So so either that might be because it's pretty subjective, but can't really rely on there being an even distance between never and maybe and some of the time. So those are the ordinal variables. There's an ordering. You can say things are greater than or less than, but the distance between things isn't a useful concept that we can rely on. Does that make sense? So we have ordering, but not really a sense of scale. Okay. The next would be interval variables. Okay. Interval variables, we are interested in the difference between things. So interval variables would be things like temperature in Celsius or Fahrenheit. Right? So not only does a higher temperature mean warmer, but the distance between two temperatures matters. Okay? The reason there's still one more level is the interval variables. It makes sense to like subtract and stuff, but it doesn't really make sense to divide. Okay? So for temperatures, why isn't division like a reasonable thing to do with temperatures?
You don't ever say like let's divide this temperature.
Yeah. So when I say like, so let's say in a month it's going to be 100 degrees. A month ago it was 50 degrees. I'd say it's twice as hot as it was a month ago. Does that make sense? Any physics people in the room want to tell me why that doesn't make sense? So there's a subjective element.
I mean, just like, 40 degrees isn't twice as warm as 20 degrees.
Why not?
0 doesn't represent the absence of temperature.
Exactly. So the 0 is arbitrary. Okay. So for interval variables, the location of the 0 doesn't really matter, okay, which means that division ratios don't really make a lot of sense. Okay. So if I was talking about Kelvin, temperatures in Kelvin or Rankine, then I could do this, right? 0 is an important measure. It's the absence of like no energy or whatever. But when I'm talking about Celsius and Fahrenheit, right, the 0 is kind of picked arbitrarily, so it doesn't really make sense. The distance from 0 isn't really a useful measure for my analysis. So these interval variables, right, the distances between things is important, but the distance from 0 is not really. Okay. And then the last type of data is ratio data. Here, 0 is important, right? So we can, division is the thing that makes sense. So the ratio between variables is something that might be important. So some things that would be considered ratio variables would be length, right? The length of 0 is important. Age, length. I already say length. Temperature in Kelvin. These are all things that would be ratio variables. So maybe let's talk through a few different things we might measure and try to categorize them. Okay. So what about latitude? So first off, would latitude be a discrete or a continuous thing? Continuous, right? You can have fractions of a degree of latitude. Okay. Which of these? Zero doesn't really matter. So is the 0 for latitude important or special? So what does the 0 for latitude tell you? What? That's sea level. It's the equator, right? So I think you could make an argument that the 0 for latitude is pretty important because especially if you're using it for like geometry stuff, right? The distance from 0 does matter in terms of distances or whatever it is you're measuring. So I think you could make a pretty good argument that latitude would be a ratio variable. Maybe you could argue that it's interval. It's clearly not categorical or ordinal. If I wanted a categorical measure of something like latitude, what would that look like? Or yeah, so we could have like Arctic, subtropical, tropical, temperate, whatever. Would that really be ordinal, probably? Or sorry, wouldn't really be categorical. Probably even that would be ordinal, right? Because there is an ordering between these things, probably. So you could either go, from distance from the equator or from South Pole to North Pole or whatever, but there's probably some sort of ordering there. What about longitude? So it's clearly neither of these, right? It's still continuous. What about deciding between interval and ratio? 0 is arbitrary, right? People in England thought they were important, right? Or France, maybe one of the two. Right. So the 0 for longitude is arbitrary, right? So that is probably more of an interval. Right? The distances in longitude are very important, but the absolute value is pretty arbitrary. It matters, but it's arbitrary. About Olympic 50-meter race times. Probably ratio, like the 0 is important, right? Yeah. Olympic gymnastics scores. Yeah, it kind of depends. I don't know that the judges ever give out a 0, so. So I would say probably here the distance between these matters a lot more than the ratio between them. I think probably I would make the case that it would be an interval, but you could argue ratio as well. Amazon rating for a product. Probably ordinal, right? You know, the difference between a 3-star and a 4-star and a 5-star might not necessarily mean the same thing. College major, categorical, unless you know the STEM majors are obviously the best, but yeah, everything else is categorical. Yeah. So yeah, the first thing we need to do before we start analyzing our data is understand what kind of data it is, so we can talk about what makes sense to do. Cool. So for today, we're mostly going to talk about things that can be applied to interval and ratio data. And so these are things that basically are floats. Maybe ints, but we're going to do like float math with them. Okay, so the first sort of category of thing we'll talk about are the descriptive statistics. And the goal of descriptive statistics is basically we have a whole bunch of data points. We would like to summarize them or describe a you know, sort of an overview of the data by representing them with a smaller set of numbers. Okay? So you're probably familiar with a whole bunch of these. What are some descriptive statistics, and what are some ways we might summarize a whole bunch of floating point data that we have? Standard deviation. What's the more common, the easier thing that standard deviation is related to? Variance is even a little more esoteric. Let's go with like more elementary school. Average, mean, right? So the mean and the standard deviation / variance. What do they tell us about our data? So what does the mean tell us? So yeah, I mean we compute it, we sum everything up and divide by a number. What does it tell us? Like I tell you the mean of some data is, what is that? What information does that provide you with? Why do we bother to compute it? Yeah, so it tells you kind of where the center of your data is, right? Does it tell you about a typical data value? Not necessarily. It might. It depends on how your data is distributed, but it tells you kind of where the center of the data is. Okay? And what about the standard deviation or the variance? What does it tell you? Yeah, how close the data is to the mean, right? So if we have a very high standard deviation, then we know that things are kind of spread out away from the mean. Right? If we have a very small standard deviation, then the mean is everything is pretty tightly grouped around. Yeah, mean, I think everybody knows the formula. Standard deviation, probably not that useful to go through the formula. You can look it up if you need, but it's going to measure how far away we are from the mean, kind of on average. The variance, does anybody know the relationship between the variance and the standard deviation?
Square root.
Yeah, so the variance is just the standard deviation squared. So you will see both of those, and basically people choose based on like which is more convenient for either computation or for sending to the next step. So when we talk about normal distributions, we talk about the variance because the sigma, the standard deviation squared, shows up in the formula. But they both tell you the same thing. It's just a matter of a square root. Okay. So those are kind of the most basic descriptive statistics we're interested in. The count is also another one, just the number of data points that we have. Pretty obvious that would be a useful thing to know. Okay. So beyond that, so the mean tells us, kind of where the center of our data is. It might not correspond to any actual data points. Right? If we want something that does correspond to an actual data point, what kind of descriptive statistic might we be interested in? The median. Right? So what is the median? It's the middle if what? If it's sorted, right? Okay. Which is going to be easier to compute, the mean or the median?
Mean.
So it depends, I guess. If your data is unsorted, the mean is going to be a lot easier. If your data is sorted, the median is going to be easier. If you were going to be naive about finding the median, what would you do?
Just
Sort it and then go to the middle. So what would be the time complexity there? Well, so
log n.
n log n, right? Unless you're either really dumb or you're really lucky. Yeah, it's going to take n log n time to sort it and then find the middle. Do you guys talk about fast order statistics algorithms in the data structures class? No. So it turns out that you can actually find the median or any what's called an order statistic, which is like the median but not necessarily in the middle. You can actually do that in linear time. If you think about it, it kind of makes sense. We don't really have to sort everything. We really just have to partition a particular spot, right? So we have to make sure that everything smaller than the median is, to the left of it, everything bigger is to the right of it. But those sections don't have to be sorted, right? So it makes sense that it would be less time than sorting. And you can do that for, whatever, if you want to know the first percentile or the 99th percentile, right? You still have to get, you have to move all of the bigger stuff to one side, all the smaller stuff to one side, and you can do all these in linear time. So that's a pretty like classic, clever algorithm that if you took another algorithms class, I'm sure you'd cover. So the median is pretty important. Other things that we're interested in related to that would be quartiles, should just be the the value where 25% is on one side and 75% of the data is on the other. So we're often interested in the median and then the 25th and 75th quartile, or first and third quartile, I guess. Sometimes we care about other order statistics. So if you are working on some sort of like web service, a lot of time you're interested in like the 99th percentile latency. So what how much time do 99% of your requests take, or less than that. So the 99th percentile is the time where like 99% of the time you're faster than that. So these are ways of describing our data, right? For that, for the latency case, if my 99th percentile latency is low, right? If 99% of the time my requests take less time than X, I probably don't really care what the distribution is in that range as long as it's less than some small value, right? So if my 99th percentile latency is 5 milliseconds, and that's fast for my application, I really don't care what the data looks like as long as the times are below that. So the descriptive statistics allow us to summarize our data so that we we can describe what we care about without showing all of the data. So those are common descriptive statistics. Two more that we are that are useful when we have multiple pieces of data and we're interested in the relationship between them are the covariance and correlation. And these basically tell us how one set of data changes compared to another set of data. The common sort of measures that we talk about and compute very often are the linear covariance and correlation. So if I have two types of data, X and Y, right? I'm kind of interested in what they look like. So if I have, my data looks like this, is there a strong relationship between X and Y? No, right? So these variables seem to be unrelated or uncorrelated. Right? Whereas if I have data that looks like this, these are strongly correlated. Right? So the covariance and correlation are ways of basically putting a number to how much these things are related. Right? So the closer they are to being a straight line with each other, the stronger the correlation, and the more kind of the further away they get from this, the less correlation. So the typical measures for these are linear, which means that if I had data that looks like this, is there a relationship between these two variables? Yes, relationships. So what? So anybody have an idea of how Y might be related to X here? This is like probably a sine or a cosine function, something like that. But my correlation and covariance would be very low, right? Because the typical measures are for linear stuff. This is not a linear relationship. And so those can be useful measures, but they're not. They don't capture everything, but they can be useful for identifying sort of simple relationships. Yeah. So we'll go through. We'll look at these in a little bit more detail a little bit later. Cool. So when we're talking about correlation, even if we find correlation, right, two variables change, are related to each other in a structured way, that's all it means. All it means is that they change in a related way. It doesn't mean that there's any sort of causation between them, right? It could mean that, but it doesn't necessarily. So when we see correlation and we want to use it to explain things, we really need to be careful and make sure that we're not being tricked by confounding factors. So an example of this is our data that we have are the number of swimming pool deaths per day, which is a really dark thing to measure. And And the other data set that we have is the amount of ice cream that's sold each day, right? We find that these two data sets are correlated with each other. Can we infer that either swimming deaths are responsible for ice cream, or that ice cream is responsible for swimming pool deaths? Probably not. Yeah. Yeah. So why, we have this correlation between our data, but it doesn't tell us really anything about the relationship between these two bits of data. So what's probably going on? What factor that is not part of either data set is probably causing this correlation? Temperature, right? So what impact is temperature having?
So higher temperature, more ice cream, and more swimming, and more for that.
Yep. So we have more swimmers and more ice cream eaters on hot days, right? So they're correlated not because there's any relationship between ice cream and drowning, but because they both share similar relationships with temperature. So we need to make sure that we sort of understand the context of our data, so we don't get tricked into thinking that there's a relationship between our data sets that is not really there. So that's kind of a quick overview of descriptive statistics. So we're trying to summarize our data to make sense of it, to shrink it down into a much smaller set of numbers that we can start to think about. Any questions about descriptive statistics? How many people have taken a stats class? Okay, so just a little review.
Like a long time.
I don't know what you guys say.
I assume your stats class was focused a lot on like the mechanics of how you compute this stuff. We're just going to use pandas or NumPy or whatever to compute this stuff for us. So it's a good idea to know sort of what operations are involved with these, but like we're not going to memorize formulas or anything like that, right? Somebody built these tools already, so we're going to make use of them. Okay, so this is descriptive statistics. We have some data. We want to describe it, make sense of it. The other sort of family of statistics that we're going to be dealing with are inferential statistics, which are a lot more interesting. The idea here is that our data, instead of thinking about it as sort of summarizing or describing a phenomenon, we're thinking about our data as samples from some larger population of data. And in inferential statistics, we're trying to learn something or understand something about the larger population based on a small set of samples. Okay? So a common, a typical example, I'm a political pollster, right? I get 500 people across the country to respond to my poll. Okay? I don't really care about summarizing what those 500 people think. Right? I'm sure they're lovely people, but what I'm interested in is knowing, based on what I heard from those 500 people, what does the whole population of the country likely think? Okay? So my job is to take this sample data that I have, right, and try to make predictions about what the larger population that I can't possibly sample everybody. I want to kind of have an estimate of what the population at large is like, just based on the sample. So that's the idea. So we're trying to take what we measure and try to kind of infer what we couldn't measure based on that. So when we talk about inferential statistics, we very often talk about probability distributions, and we'll get to calculus and all that stuff. But kind of the key the key concept that we deal with is a random variable. So a random variable is basically a variable that has sort of many possible values, okay? And we can sample that random variable to get one of the possible values out. Okay? So an example of a random variable would be a die. Okay? Okay. If we have a fair die, right? There are 6 possible values I could get, right? Each with hopefully equal probability, right? So if my die is a random variable, I can sample it by rolling it and see what I get, right? Okay. And from those various samples, right, I could try to learn the whether my die is fair or not, or other information about what's going on. Okay. So the random variable, right, is kind of the basic building block. So if I have a data set, basically the way I want to think about it when I'm doing inferential statistics is my data set is a bunch of samples from a particular random variable that I'm trying to understand. That kind of makes sense? We have, these can be discrete or continuous, right? So a die or a coin would be examples of discrete random variables. Any thoughts on continuous random variables? A little trickier because I guess the board games we all play usually work with discrete stuff. If you think of a dartboard, not with the rules of darts, but just as a geometric object that you throw something at randomly, right? The position of your dart in a dartboard you could consider as a random variable. If I'm playing, it's a random variable. Right? So it could take on many possible different values, right? So it would be a continuous random variable. So some things we want to do with random variables are sample them, right? There's a bunch of distributions which describe the values we would get out of a random variable, that we could get out of a random variable and the probabilities associated with them, right? So one thing we want to do is just get a bunch of values from a random variable. So this would be like rolling a die a bunch of times and just tallying up what I get out. So that's one thing we might want to do with them. Another thing we might want to do is, from a bunch of samples from which we don't know what the distribution is ahead of time, try to figure out what the probability distribution looks like based on the samples. Okay. So example of that is is the political poll, right? We call up a bunch of people, we figure out which candidates they like, and then we try to figure out, okay, assuming that each one of those people is a sample from a random variable, what does the probability distribution look like that gave us those particular samples? And we're trying to infer what the probability distribution looks like from the samples that we were able to collect. Okay. We'll talk about some particular tasks related to sort of trying to understand probability distributions based on data. We'll talk about that tomorrow. So one of the simplest and most common tasks that we'll have is called a hypothesis test. And so we, in that case, we're trying to see if, does it make sense for us to collect this data if our hypothesis about the population is true. We'll talk about that in detail tomorrow. But before we can do that, we kind of have to understand what are the various shapes of probability distributions that we can deal with. And we will use those tomorrow once when we talk about hypothesis testing. The first probability distribution we'll talk about is called the Bernoulli Distribution. Bernoulli was very lucky that he was the first one to come up with this. Bernoulli distribution is a coin. So he gets his name in every stats class ever for coming up with the idea of a coin. So basically, the Bernoulli distribution describes a coin flip. Okay? So there's two possible outcomes, right? Heads or tails, we'll call them 1 or 0. Okay? And basically what we're going to say is the probability of heads is P, and we're going to say that heads is 1. Okay? So what's the probability of tails? Heads is P, 1 minus P. Right? So P of tails is 1 minus P. Is this a random variable a discrete or a continuous random variable? Discrete, right? There's only 2 values, heads or tails. Okay. If I have a fair coin, what's P?
0.5.
It's going to be 0.5, right? If I have an unfair coin, right, it would be something else. Okay. Right. So this is the Bernoulli distribution. So for this distribution, for all these distributions, we're kind of interested in a little bit about the expected behavior of the coin. So what do we expect the mean of the Bernoulli distribution to be? So if I took a whole bunch of samples, right, what is the expected value that we think we get out?
0.5.
So it depends. So it's probably not always going to be 0.5. If I have an unfair coin, for example.
1 divided by n.
So one thing. So this is a discrete random variable, but if I kind of think about it through a continuous lens, right? If I flip a coin, right, the value I kind of expect to get is P times 1 plus 1 minus P times 0. That kind of makes sense. So if I think about like, you think of like some sort of quantum thing where all these things are happening at once, right? My expected value is P times 1, right? I have a P% chance of getting heads, right? And a 1 minus P chance of getting tails, right? And so my expected value is just going to be P, right? And so the mean of this distribution is actually P. And so if I do a bunch of trials, right, I expect to get, I get 1 P% of the time, 0, 1 minus P% of the time, and if I add it up, I get mean of this distribution. The other thing we care about is the variance. Okay, so, I expect to get both heads and tails accordingly. So the variance is actually P times 1 minus P for this distribution. have this formula here. Can anybody kind of make sense of this? How does the variance change with P? When is the variance the highest?
The higher.
So I'm going to do a little bit of calculus here.
So when P equals 1 minus P will be highest.
So we have P minus P squared. Just expand this out. If I want to know the maximum, I might remember calculus. How do I figure that out?
Can you draw the graph and
I could draw the graph. Yeah. If I just want to do some calculus, how do I find the maximum with some calculus? Nobody remembers.
minus
The
P
integral.
squared?
Integral is not the integral. The opposite of the integral. Derivative. If I take the derivative, how do I find the max using the derivative?
Derivative equals 0.
I'm going to take a quick derivative, set it to 0. Okay. So this is my derivative. And if I set this equal to 0, I find the max is going to be at P equals 1/2. So if I have a fair coin, I'm going to have the most variance of any coin. As I make my coin more unfair, I expect there to be less variance. So if I have a coin that's heads heavy, right? If I flip it more, I'm going to get heads most of the time. It's going to be less common that I get tails, right? And so my variance is going to be lower, right? My mean is more heads-like, right? I'm going to have fewer tails, right? So my variance is going to be lower, right? If I have a super unfair coin, right? If I have a coin that never comes up tails, right? My variance is going to be 0, right? I get heads every single time, right? And so the more fair my coin is, the more variance I expect, right? Because I'm going to have a mix of heads and tails. That kind of makes sense. So this is the Bernoulli Distribution. Okay. It models a coin that could be fair or unfair. Right? This is kind of the simplest probability distribution. Cool. Any questions about that? This seems kind of like a lot of nomenclature for talking about a coin, but as we get to more complicated things, it's kind of useful. The next distribution we're interested in is we take the Bernoulli distribution and we basically flip a whole bunch of coins, and basically we just want to count the number of heads we got at the end. Okay? So the Bernoulli distribution helps us make the binomial distribution. Okay? The idea here is basically this models the number of heads in n coin flips of a coin with probability P. Okay. So this is a Bernoulli coin, right? With P could be 0.5 if it's a fair coin, or something else if it's not a fair coin. Okay. In the binomial distribution, I say I'm going to flip this coin n times. How many heads do I get? That kind of makes sense. So let me just draw kind of a graph of what we think this is going to look like. Okay. So let's assume n is pretty big. What should the kind of bounds on my axes be? Like how far should my x-axis go?
0 to n.
0 to n, right? I could get 0 coin flips, or 0 heads. I could get n heads. I couldn't get more or less. I can't have negative heads. Okay. And so let's say my probability, let's say I have a fair coin. What do you think the graph of this is going to look like? normal distribution. What does a normal distribution look like?
Like a bell curve.
Bell curve, right? So we'd expect that what's the kind of the most probable number of heads that we would get? N over 2, right? We think it's probably the most likely, right? And as we go further away, right, we expect it to be, less likely. There's still some probability that we would get heads every single time, but not very likely. So for a fair coin, it would look something like this. What if I have a coin that's pretty biased towards heads? Let's say my probability is like 0.75. Where's the peak going to be? It'll be over here. This would be P equals 0.5. P equals 0.75. Right, I'm going to have my peak here. Right? It might look something like that. So I just flip a coin a whole bunch of times. I count how many heads I get. Right? The expected value that I would get out is is P times N, right? And then the curve, kind of looks like you'd expect. If N is really small, what is the shape of? Does this picture make sense regardless of what N is? Actually, not really. So the general shape is kind of the same. If I make N really small, what's going to happen? So let's say my N was 3, or let's say my N was 2. N was 2. My expected value, if I flip a coin twice, I would expect to get 1 heads. Right? What's the probability that I get no heads? I get tails twice. A quarter, right? 0.25, right? If I get 2 heads, that's 0.25, right? So if N is 2, this is like pretty flat, right? If N is 100, what's the probability that I get 0 heads? Like really, really, really small, right? It's 1/2 to the 100, right? Really, really small, right? Probability that I get all heads, really, really small, right? So as N gets bigger, this distribution actually gets really, really steep and narrow in the middle, and the probability is really low far away. So if I have a big N, right, this looks more like that. Right, so both the P and the N actually have a big impact in the shape of these. Right, P kind of tells us where the hump is and sort of where we go up and down. Right, N tells me how sharp that peak is, and a larger N is going to be really, really tight peak. So is this binomial distribution? Is this a discrete or a continuous distribution? So what is the value that I'm getting out of this distribution? I sample it, what do I get? I say, give me a value from the Bernoulli distribution, what do I get back?
The probability in a given.
So when I sample, I don't get a probability, I get an actual value out. So which value I get depends on the probability, but what is the thing I get out sort of represents? So what I get back is the number of heads that I got when I flipped the coin n times. Right? So is that going to be a discrete value or a continuous value? Discrete, right? I can only get whole numbers of heads out. Right? So even though I drew this as a curve, right, I'm still dealing with a discrete probability distribution. I can only get the integers from 0 to n. Does that make sense? So this is an example of another discrete probability distribution. It's built on the a simpler discrete distribution. So this is another discrete distribution. Okay. So when I'm dealing with discrete probability distributions, I'm interested in basically the probability of each outcome. Okay, so I'm interested in the probability of 0 heads or 50 heads or 75 heads, whatever. Okay? And when I'm dealing with a discrete probability distribution, since there are only a finite number of possible outcomes, there are, I can basically compute exactly the probability of each of these things happening. Right? So we did that with the coin case, right? For the probability of getting 0, or of getting, let's say, n heads is p to the n, right? Each flip, there's a probability p, I do that n times, right? For the other values, it's a little bit more complicated because of the order in which I flip the coins. I have to take that into account, right? But I can, I can do the math. I can figure out what the probability of each possible outcome is. Right? And if I do that, I get what's called the probability mass function. And the probability mass function tells me for a given value that I could get out of this distribution, what is the probability that I get that value? Okay? So let's say I have a die, right? The PMF of x, if x is 1 to 6, is going to be 1/6 for a fair die. Right? So I plug in any x, the probability of getting a 3 is 1/6. Probability of getting a 6 is 1/6. Okay. So this tells me the probability mass function. Okay. How about for a Bernoulli variable? So here, basically, there's what are the possible inputs I can put here that make sense?
1, 2, 6.
For the Bernoulli, heads or tails, right? So 1 or 0, right? So x equals 1 or x equals 0. So for x equals 1, what's the probability that I get that, that if I do my trial, I get a 1 back? It's part of the definition of the Bernoulli distribution. The probability of getting a 1 is p. The probability of getting a 0 is 1 minus p. So this is just the definition of the Bernoulli distribution. Okay. So this is my probability mass function. Right? This tells me if I'm interested in what are the chances of getting such and such value, right? Then this tells me what that probability is. Does that make sense? How about for the Bernoulli? Or sorry, the binomial. Any thoughts on this? What are some pieces that kind of should be in here? So what is it, so PMF of x means I got x heads from my coin, right? It also means I got n minus x tailses, right? So maybe we can start with that. So what's the probability of getting x heads, or a piece of how we would get x heads out?
Be like 1 over x to the n.
So for a particular trial, what's the probability of getting heads?